We're continuing with section 15.1 and let's discuss how to integrate over a rectangular region. As you see here, basically the blue little slab that goes around the volume, it actually is another way of dividing the entire volume into infinitesimal little volumes. And so each one of these blues, and it's moving because it shows you it can be at any point on the under the surface. Each one of those is actually and it has infinitesimal width, but then you can find the area of the region inside the blue with a calc1. It would be a calc1 question to find that area, then multiply it by the width that is infinitesimal and get the entire volume. So basically you want to do in calc1 integration. Here though it's not going to be the calc1 integration depends on where you are on the alongside the x-axis, and then you do another integration, calc1 integration, to basically add all these little slabs, these little piece of volumes together. So you can do it either first in the x direction and then add them up in the y direction, or no, sorry, in this case it was first on y direction and then on x direction, or you can switch the side. So the slab can basically they themselves be alongside the x direction, then you add them all up in direction of y. So this one, the red is spread along the x-axis, but it travels, all the different ones are traveling along the y-axis. So inside is one way, outside is one way, and then here the slab itself is along the y-axis, and all of them are adding up along the x-axis. So this is another way of basically keeping a track of the Riemann sum that is within with the little pieces of volume. So evaluating integral, the intuition, we discuss it on the GeoGebra sheet, how basically we divide the Riemann sum into two calc1, and we divide them into two problems of calc1 nature. Now let's talk about it more formally. Assume f of x and y is bigger than or equal to 0. Again, we're still doing it that way later on, area above minus area under. Let W be the solid region below the graph of f of x and y, and above the rectangle R equal to A and B times C D. Now we can cut W into slices, Wx for every x in A and B. And these slices, look at this slice, it's sitting on the basically alongside the y-axis. You can compute the area of that slice, the thin slice, so infinitesimal width, and then you find the area and multiply by infinitesimal width. And that area is basically integral from C to D of f of xy if you set the y, set the x equal to a constant dy, basically. And so when you're writing integral like that, even though x is present in there, x is going to be considered a constant. Now, the entire volume, so each area is going to be that for different x. The entire volume is going to be integral of that a of x over basically 0 a to b. Why? Because x changes from a to b, and your integral is basically adding them all together. And so you will have integral from a to b over x of integral from c to d of f of x and y dy, basically. And so you compute the inner integral, and then you can use that as the function for the outer integral. That would be iterated integral. And so from the picture we saw, from the GeoGebra sheet that we saw, we realized that we can switch side. And this one is that story. So assume f of x and y is bigger than or equal to 0. Let W be a region below the graph of f of x and y and above the rectangle R equal to a and b times CD. We can cut W into slices, WY for each y in CD, in the interval CD. For a fixed y, the slice WY has the area B of y equal to integral from a to b of f of x and y dx. The volume of W is the integral of the cross-sectional area WY. The volume of W is equal to double integral on region R of f of x and y over the A element, A infinitesimal area element. And this is basically the integral from C to D of B y dy, the slabs. And then so rewrite the b sub y, and you see the inner integral is the one variable integral of f of x and y dx from a to b, and then the outer integral uses that function and integrates that from c to d over dy. So the entire mystery of dA is solved. Now you know that dA basically breaks down into dx dy or dy dx. The other thing is that you notice that every time you have two variables, you have to set one of them equal to a constant, then take the integral, and you can change the order of the integration. So let's put it more formally. All the discussion that we had, somewhat formal discussion of proof, into a theorem, and that's called Fubinni's theorem. Fubinni's theorem says if f of x and y is continuous on a rectangle R equal to AB times CD, then the double integral over the region R of f of x and y is equal to integral from x equal to a to x equal to b of another integral dx, and that other integral is y equal to c to y equal to d of f of x and y dy. Or you can it's equal to if you switch the integral. So integral from y equal to c to y equal to d, and over y of another integral, function is another integral, from x equal to a to x equal to b of f of xy dx. Things to notice, in the beginning especially, instead of writing integral from a to b, we have to remember to write integral from x equal to a to x equal to b, because x is changing for the outer one. And then for inner one, you go y equal to. It's very helpful for the next section also to put it this way. In a lot of confusion about what gets to be going to what is going to go away using that. The other thing is that we always put it inner integral in a parenthesis, so you remember it creates a new function, and you take the integral of that with respect to the other variable. Basically, you're breaking down integral in two variables into two integrals of one variable, and one inner integral and one outer integral, according to all the stories that we told. The integrals on the right hand sides are called iterated integrals. And again, to evaluate the integral, let's say integral from a to b, integral from c to d of f of x, y, dy, dx, evaluate the inner integral for y by treating x as a fixed parameter. The result of integral from c to d of f of x, y, dy is a function of x. Then evaluate the integral with respect to x. And so the other way around is just all those variables are gonna switch basically. Let's do iClicker question 15.1b, which of the following is equal to the integral from 1 to 2 of integral from 4 to 5 of f of x, y, dy, dx. So give yourself a minute and think about it and come back. So if this is an iterated integral and the order is the inside is with respect to y and the outside is with respect to x, what I'm expecting is the other way around. So I want to look at all the dx dy's, right? And when I do dx dy, the integral bounds have to switch with the y. So here y is matched with 2 and 1, which is y over here is matched with 4 and 5. So this one is out. Here y is matched with, again, 2 and 1. And 5 and 4 is switched. It's just not the same thing as that one. Over here, y is matched with 4 and 5 in the right order, and x is matched with 1 and 2 in the right order. So D is the answer.